Okay, guys, today we're going to go over polar versus nonpolar molecules, okay, not to be confused with polar versus nonpolar bonds, okay, and we are on page 16 of our notes, okay, so this is polar and nonpolar molecules. So in chemistry, if something is polar, it means that there is an unequal distribution of electrons, okay, we know that a polar bond means that the electrons are heavier on one side than the other, okay. Previously, we learned about polar and nonpolar bonds. Okay, we learned about polar and nonpolar bonds. Now we're going to learn that it is possible for an entire molecule to be considered polar or nonpolar. Okay, so an entire molecule. That's what we're learning about today. Okay, so let's talk about what a dipole moment is. A dipole moment, a polar bond has an unequal sharing of electrons. We already know that. Okay, we already know that about polar bonds. Okay, for example, in HCl, the electrons of the electronegativity of the chlorine is 3.0. The electronegativity of the hydrogen is 2.1. Basically, all you need to know is that chlorine has a higher electronegativity, which we know because if we look at this periodic table, if we're looking at fluorine versus hydrogen, chlorine. We're looking at chlorine versus hydrogen. Chlorine is closer to fluorine, making it's going to have a higher electronegativity. Okay, so that follows that trend. As we go to the right, our electronegativity increases. Okay, so we know chlorine has a higher electronegativity. The result is a bond where the electron pair is displaced more toward the more electronegative atom. Okay, so the more electronegative atom. This atom obtains what we call a partial negative charge. Okay, a partial negative charge, while the less electronegative atom has a partial positive charge. Okay, the separation of charge or dipole moment, okay, so separation of charge or dipole moment can be illustrated using an arrow with the arrowhead directed towards the more electronegative atom. Okay, more electronegative atoms. So let me describe what I'm talking about here. So if I ever have a bond between two things, and it's a polar bond, okay? If it's a polar covalent bond, then we can draw an arrow to represent where the electrons are spending most of their time. Okay, where are the electrons spending most of their time? They're spending most of their time with chlorine because chlorine has a higher electronegativity. Chlorine has a higher electronegativity. So that's the direction the arrow is going to point. Electronegativity. Okay, electronegativity. Okay, so the electrons are going to spend more of their time with chlorine. Because they're going to spend more time with chlorine, it's going to have a partial negative charge, and the hydrogen is going to have a partial positive charge. This weird little squiggly line is a lowercase Greek letter delta, and it stands for partially. Okay, so it's not a full-blown negative charge because this isn't an ionic bond. It's a covalent bond still, right? It's a covalent bond, so we don't have full-blown charges. But it's kind of like a pseudo-negative charge because while the electrons aren't being transferred from hydrogen to chlorine, they are spending more of their time with chlorine than they are with hydrogen. So they're still sharing, but they're not sharing very equally because chlorine is hogging them a little bit more often, so it has what we call a partial negative charge. Okay, so the Greek letter delta indicates partially. Okay, so within each molecule, each polar bond has a dipole moment. So this exists within each bond. Within each polar bond, we have what's called a dipole moment, or basically just an area where the electrons spend more of their time. Okay, so polar molecules. Now let's talk about polar molecules. So this is polar bonds. Let's talk about polar molecules. A molecule, an entire molecule in which the bond dipoles present do not cancel each other out and thus result in a molecular dipole. Let's highlight that, molecular dipole. Okay, cancellation depends on the symmetry of the molecule and orientation of the polar bonds. Okay, so molecular dipole is a result of the bond dipoles in a molecule. Bond dipoles may or may not cancel out, thereby producing either molecules that are nonpolar if they cancel, or polar if they do not cancel. For example, CO2 is a linear molecule with two bond dipoles that are equal and oppositely directed. Therefore, the bond polarities cancel, and the molecule is nonpolar. So even though CO2 has polar bonds, so this bond is polar, this bond is polar, even though the bonds are polar, the entire molecule is nonpolar. So polar bonds, nonpolar molecule, because they cancel, the polar bonds are going equal and opposite ways. Nonpolar molecule. So it's possible to have polar bonds and the overall molecule nonpolar. Now, there's something I want to point out. I almost forgot. A lot of the time you'll see these arrows with a little like plus sign at the end of them. And I'll put that up here as well. Draw a little plus sign on your arrows, a little line there that makes it look like a plus. And so that helps us remember, the thing with the positive charge is the side with the plus sign, and the arrow points to the negative charge, or the more electronegative element. Okay? Okay, and how did we know that the arrows point out and not in? How did they know that? Well, you're always going to point to the more electronegative element. So if we have carbon and oxygen, oxygen's more electronegative because it's further to the right. It's closer to fluorine. As you go to the right and up, the electronegativity increases. So because oxygen's closer to fluorine, it's going to have a higher electronegativity than carbon, and that is why the arrows point to oxygen. You point to the more electronegative element. Okay, flip it over. Okay, so how do you know if a molecule is polar or nonpolar? So here, if you guys didn't understand anything I just said, you're in luck, because this sentence summarizes everything and makes it really easy. So I gave you all the background. Now let's do the practical application. Here's our summary. If there are any lone pairs, around the central atom, the molecule is polar. If there are no lone pairs around the central atom, and it is a symmetrical molecule, it is nonpolar. Okay, so this is basically all you need to know. So let's practice. So I'm going to look at this molecule. Are there any lone pairs around the central atom? No, there are not, because carbon is our central atom. There's lone pairs around here, but those are not carbon. We're just looking at the central atom. If there are no lone pairs around the central atom, okay, no lone pairs around the central atom, then it's not going to be polar. So if there's no lone pairs around the central atom, and if it's symmetrical, it's nonpolar. So is it symmetrical? Yeah, it's symmetrical. It's the same on both sides. We both have sulfur on both sides. So this is going to be nonpolar. Okay? This one. Are there lone pairs around the central atom? No, there are no lone pairs around boron. Is it symmetrical? Yes, it's symmetrical. It's just fluorines all around. This one's also nonpolar. Oops, nonpolar. Does this have lone pairs around the central atom? No lone pairs around carbon. Is it symmetrical? Sure is. It's just surrounded by chlorines. So this one's also going to be nonpolar. Does this one have lone pairs around the central atom? Yes. Yes, it has a lone pair on nitrogen. Because it has a lone pair on nitrogen, it's going to be polar. Okay, because if it has a lone pair around the central atom, it's polar. Okay, and are there lone pairs around the central atom? Yep, so this one's going to be polar as well. Okay, and the reason why it's polar is it basically means that their electrons are spending more time on one half of the molecule than on the other half of the molecule. Okay, this half of the molecule is going to have more negatives going on because there's more electrons over here than over here. There's more electrons over on this side of the molecule than there will be on this side, so it's uneven. Whereas these ones, the electrons are evenly distributed. Now, this would be different. So these are true for these shapes. So linear, trigonal, planar, tetrahedral, they're always going to be nonpolar. Trigonal, pyramidal, and bent are always going to be polar. The only exception to that is for these ones. Let's write this down. Unless asymmetrical. Unless they're asymmetrical. Okay? Unless these guys are asymmetrical. And what I mean by that, asymmetrical is like if this, instead of a chlorine, was suddenly like a hydrogen, just one of them. If like, it was like chlorine, 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 hydrogen, that would no longer be symmetrical. That would then become polar. Okay? That's what I mean by that. Okay? All right. That's all I have for you guys. What you're going to do now is you're going to find this video. So if you go to YouTube and just literally type in like crash course polar nonpolar, or if you want to type in this exact thing, you can. And you should find there's a crash course video where he goes over polar and nonpolar molecules. Very interesting. I enjoyed it. It's kind of fun. And then I need you to take notes here on some things that you learned. Okay, this shouldn't be blank. It should show me that you've actually watched the entire video and you learned some things and that you wrote some things down. Okay, show me that you learned from the video. And then you guys are going to take pictures of these notes. Okay.